Hello, everyone. My name is Filippo Simini, and I am a member of the data science team at ALCF. And welcome again to the ALCF AI for Science training. This is the second session of 2022, and it's going to be about deep generative models, specifically on generative adversarial networks and autoencoders. And the speaker of this session is Corey Adams. Here on this page, you have all the information about the session, and the session is going to be recorded. So in a few days, if you scroll down on this page, you will find a link to the video recording as well. If you go to the main page for the program, you find all of the past and future sessions and links. And if you missed one of the previous sessions, you can click and scroll all the way to the bottom and find the video recording for that one. Another useful resource is the Github repo of the sessions, where you can find all of the useful material and code and information regarding each of the sessions. So on the Slack channel for the current session, you can find both the link to the GitHub repository and to the web page I showed earlier. You can, my advice is to follow along with the speaker. And so when you log into the Theta GPU machine, you can either clone the repository or do a Git update of the, in order to have the most recent version of the repo and all of the files and the code. Both the links, as I said, are on the Slack channel for today's session. In the introductions to the sessions, we would also, let me switch the, so in these introductions, we would also like to inform you about opportunities and initiatives at Argonne, as well as let you know about ongoing research at the laboratory. Today, I'll give you a short 5-minute summary of 2 of the projects I'm currently working on in collaboration with colleagues at Argonne and at other institutions. The first one is about anomaly detection in large data streams. The second is about coupling simulations and online learning at scale. So the project about anomaly detection is in collaboration with Swift, which is a company that provides financial messaging services and currently process more than 95% of all financial transactions in the world. So how does it work? So if a customer at Bank A wants to send money to a customer at Bank B, then this message goes through the Swift network, which is a network of banks. So it can go either directly from Bank A to Bank B, or can go through other intermediary banks, as is often the case, for example, for international transactions. So the project goal is to develop and explore AI models to detect anomalies. In this case, we're interested in detecting frauds in the Swift transaction data. We want to do this also providing end users with an explanation for the model's decision to classify a given transaction as fraud or not. And also, since this deals with sensitive information, we want to do this without revealing preserving the privacy of users and of the Swift proprietary information. So the methods that we are currently using for the anomaly detection include both classic machine learning models like XGBoost, which require to engineer relevant features in collaboration with domain experts in security, as well as deep learning models like temporal graph networks, which is a recently proposed model for deep learning on dynamic graphs, which should allow to automatically extract relevant features from the raw transaction data and have and build a rich temporal representation of the interactions between the banks. Other interesting aspects of the project involve the generation of synthetic dataset of financial transactions that should look statistically the same as real transactions in order to be able to produce dataset that can be used and shared publicly. And also we're exploring explainable AI techniques and as well as privacy preserving AI methods. The second project I wanted to talk about is coupling simulations and online learning at scale. The setting here is we want to simulate, we have large simulations of turbulent flows like the one you see on the top right around the tail of the vertical tail of an aircraft, which could improve engineering design of future aircraft and efficiency. And to do so, direct numerical simulations or Navier-Stokes equation are not feasible for such large systems. So cheaper methods and approximated methods like the LES methods are required, which require as well to model some of the smaller scales that those models average out to speed up computation. These models are usually machine learning models, but to train those models offline is usually difficult because snapshots of the simulation are very large, and so the training of the models has severe input-output bottlenecks. So the solution would be online learning in order to avoid writing to disk and reading from disk this large simulation snapshot. But that's something usually difficult to do because simulations and learning are usually using two different programming languages, the simulations in C, C++, or Fortran, whereas the machine learning is usually done in Python. So to overcome these problems, we are using the SmartSim framework, which provides an in-memory database that can be easily accessed from Fortran, C, C++, and Python, and with minimal modification to the code of the simulation and the learning. It allows to the data producer, the simulation, to upload data to this in-memory database, and to the data consumer, the learning side, to retrieve this data in an asynchronous manner. This infrastructure is also modular, so can be easily expanded and scale out to large HPC workloads, and also allow for do model inference and data manipulation directly on the database. And so that's the solution that we are exploring right now. So I stop here, and without further ado, I let Corey start his session on generative deep learning models.
Thanks, Filippo. I'd like to share my screen. Okay, good afternoon, everyone. So I'm Corey Adams. I'm going to talk to you today about autoencoders and generative adversarial networks, which are both examples of generative models. For today's session, I've prepared 2 Jupyter notebooks. I would encourage everybody who is logged on to grab a node on Theta GPU so you can follow along and run these yourself. If you can't get access or have problems, please ask in the Slack channels, and I'm sure someone will be able to help you. In general, generative models are a pretty challenging and unique area of machine learning in that it's typically considered an unsupervised learning task. We take a data set which does not need to have labeled images, and we try to create models that can generate more images as if they were part of the original data set. You've probably seen these in the world around you. You know, a model that can take an image of you and turn you into an art picture or a painting is an example of a generative model, where instead of generating a new one from the original data set of you, it's transferring it to a different style. The first one we're going to talk about, autoencoders, is actually something like a compression algorithm, but part of it, if you look at just half of what we're going to do, is a generative model. So it's the simplest case. We'll start there. Anyone who is following along, it's this autoencoders notebook. It's inside of the AI science training series in 05 generative models. And just so you can run things, I've got this Conda 2021-1130 kernel going. Any of the Conda modules should work for this. It just needs TensorFlow and NumPy, things like that. Okay. So an autoencoder in particular is traditionally thought of sometimes as a compression algorithm. So we take 2 models that work together. One is the encoder and one is the decoder. The encoder model's job is to take an input image and compress it. So, and it doesn't necessarily have to be an image. It can be any type of data, but it takes input data of high dimensionality and compresses it to a low dimensional feature vector. I think you've probably learned about principal component analysis in a previous session. It's the same idea here, where principal component analysis uses this eigenvalue decomposition to figure out what are the most important features of a data set. In an autoencoder, we're going to use machine learning to just make up its own features as what's the most important features of a data set. Once we have an encoder, we tack on another model called a decoder, which looks at that feature representation and low dimensionality and tries to reconstruct it to high dimensional image, back to the original image, in fact, with as much precision as possible. Of course, it's impossible to have perfect image reconstruction, but as you'll see today, the autoencoder method can get quite good. Okay, so we're going to work on the MNIST data set. Sorry, this is a typo between 0 and 9. So just the first thing you should be doing in this notebook is loading all of your TensorFlow, NumPy modules, and as well, this is how we'll load this data set. So MNIST can be downloaded directly from TensorFlow. And here I'm converting it from integers from 0 to 255 into a range of 0 to 1 in float format. I actually throw away the Y values for most of this notebook. It's an unsupervised learning problem. We don't care what the labels are. Okay, so to teach you about autoencoders, we're going to build some models in Keras, and this is going to be in sort of an object-oriented fashion. So we're going to start with this class right here, which I've called ResBlock or residual block. This is based off of the ResNet paper that won ImageNet probably 5 or 6 years ago now. It's called a residual module because it takes your input, applies some feature transformation to it, and adds it back to the original input. It turns out this is a good building block for deep networks. The networks I'm going to show you today are not necessarily deep, but this is a sort of a generalized technique for constructing larger networks. So this component, this building block itself, has 2 convolutional layers in it. I've used 3x3 kernels, and the number of filters that come in is just a parameter of this class. So it's in here in this init function. And I'm using the rectified linear unit activation. for all of this. Oh, sorry, no. Yes, activation is there. I'm also using batch normalization, which again is probably overkill for a problem like this for the MNIST dataset, but in general, this turns out to be a good building block of deep neural networks, so I've kept it in. The call function in Keras, if you're familiar with it, takes the inputs and then you can apply your layers in whatever order you like. So I apply the convolution, a batch norm, an activation, a convolution, a batch norm. This is the residual part where I take the output of that batch norm and I add it to the inputs here. So it's getting added back to the original input to this layer. It goes to the final activation and then it gets returned. So let me run that. All right. For the encoder, if you recall, the goal of the encoder is to take high resolution input and map it down to lower resolution input. So that's often called the latent space. Here, it's a parameter. You can set it. The default here is 10. I think I use 20 lower down in the notebook. The size of this dimensionality will restrict how well your autoencoder can do. So if you set this latent size to 1 and train for a very, very, very long time on MNIST, you can get decent encoding of the training set. It'll work pretty well, but it will, in fact, over-specialize and overtrain. Because you've restricted each image to be a single floating point number, you'll end up with a huge range of values along the real axis. And that's pretty much useless for generically encoding these data. So you want your latent size to be big enough to represent your data set and small enough to actually give you some compaction. If you're following along, I encourage you to try adjusting this to a different value from what I have. So I set it down here, latent size equals 20. If you'd like, try going higher or lower and see how that affects your results. You'll be able to see on my screen what the default results are. This network here, this is a typo, it should be 3 by 3. It applies this residual block network. Then it has a pooling layer where it takes it from 28 by 28 images in MNIST to 14 by 14. There's another residual block, another pooling, another residual block, and another pooling. And then finally, there's a dense layer. And this maps the output of this pooling layer to as many units as we have in our latent space. And I don't apply any activation to this. I just let it pick whatever normalization it wants for that final layer. And then in the actual call function, it goes through these in the order I mentioned: encoder, pool, encoder, pool, encoder, pool. This flattened layer allows it to map from this 2D pooled image into something that can go into a dense layer. And then I reshape it just to be sure that it's the right shape from whatever the output of is this to batched by the latent size. Okay. The decoder on the other side has the opposite job. So it needs to take in input of some form and map it back out to our original image shape. So this came down to something that was about 3 by 3 or 4 by 4 once you've divided by 28 to 14 to 7 to 3. This comes in and it has a dense layer which will map whatever the latent space is to 3 by 3 by 64. So it multiplies all these numbers together, and then I do a reshape to actually make them into images. After that, I'm using the same residual block format. So it takes this mapped latent space, applies convolutional layers to it, and then it upsamples. And the upsampling I use is this interpolation. So this is really just resizing the image by a factor of 2, and all of the pixels in between your original pixels get equal to the averaged value of the real pixels around them. So this is a way to upsample without introducing features that you might see with something like a shrouded convolution. This continues a couple times, so a residual block and an upsampling layer and a residual block, And then there's a final convolutional layer. And this is what's called a bottleneck convolution because the filter size is 1. I'm sorry, the kernel size is 1 by 1, and it brings out 1 filter in the end. So after this layer, the image will be 28 by 28 by 64. And this essentially applies an MLP to each pixel, the same MLP to each pixel. The kernel size 1 by 1 means it only looks at a single pixel at a time, but it sees all 64 filters, and it brings it down to 1 single filter. Okay, the call function here has another important step. It's not shown in the init function of this network. So as before, it goes through all these operators in order. So it gets the dense layer to map it to this 3 by 3 by 64 space. And then it gets reshaped into something that looks a bit like an image. This resize function is an upscaling function. And then it does a decoder unpooling, the final decoder layers, and then there's a sigmoid function. The sigmoid function, if you recall, maps every number that it gets to the range of 0 to 1. So really large negative numbers go to 0, really large positive numbers go to 1, and at 0, it's about 0.5. So what this function's role is in this network is because I mapped the MNIST data set to a range of 0 to 1, this sigmoid forces whatever the network spits out to the range of 0 to 1. So this lets it have a little more freedom in the total amplitude of the decoding layers. It can, if it's really sure that it's going to be a high pixel value, the decoder can predict something really high, and the sigmoid will map it to the right range. All right, questions on the network architectures, why I am using these layers, how I put it together, how it runs, anything like that? Great. So I'll create an instance of each of these networks. I've used a latent size of 20. You can see I'm on Theta GPU with the A100 GPUs. TensorFlow has noticed that. So that's good. I'm glad it's using the GPUs. And now I can inspect the modules. So I can look at the encoder.summary. This print function isn't entirely necessary here, but it's showing me all the parameters in my model. So the residual block holds all the parameters. The max pooling, of course, has no parameters. That's a fully parameter-free function. And then there's several more residual blocks, and the total parameters are about 200,000. And there's a number of non-trainable parameters in this network. That comes from the batch norm layers. So the batch normalization operators have moving means and averages, as well as deviations. And those are learned by the network by looking at the data sets that it sees, but aren't actually trained by the backpropagation algorithms. So when you see non-trainable parameters, that's what it's referring to. The decoder summary as well, it's as you expect, the dense residual block layers and a number of non-trainable parameters that are coming from the batch norm. And if you run this right away, you can print the intermediate state. Here it is. The numbers are ranging from, minus a little bit to plus a bit, generally around, -5 to 5. And if you look at it with matplotlib, it's just noise. And the decoded image, if you run it right away, it looks like this. So that doesn't look like any handwritten digit that I've ever seen. But at least the pixels are generally varying somewhat smoothly, which is something we want to mimic in the end. So it's good that our network reproduces that off the bat. All right, so training the autoencoder. In the end, we want the encoder to be as close, the decoded image to be as close to the original image as possible. To do that, the appropriate loss function is to look at every pixel coming out of the decoder and compute the mean squared error of that pixel to the input pixels. So in Keras, that's exactly the mean squared error loss. And you can train it with any optimizer you like. I've picked Atom. I pick Atom for most of my tasks because it's generally quite efficient. After that, this is all just to make some plots along the way. I can go through all of this, but it's not critical to the machine learning aspect of this problem. All right, so the actual training loop, for some number of epochs, it's 10 In this example, if you're on the GPUs, 10's a pretty good number with a batch size of 256. If you're running elsewhere, like your own laptop or something like that, I recommend you reduce this. It'll take a long time to train with just 10. All right, so the first thing I do is I shuffle the training data, and then I loop over the batches. So I pull some number of batches out based on the batch size, and I go through in the order of which I've shuffled the input data to. I reshape them to make sure they're the appropriate shape for the network. So it's batch size, 28 by 28 is the MNIST image size, and I've added this one here at the end to represent one single input filter. So an RGB image would be 3. This is black and white, so it's just 1. And this is what actually TensorFlow will use to compute the next layer of filters after a convolution layer. I need to keep track of the gradients in this part. So this is where the networks are actually applied. So I use this syntax in TensorFlow with tf.gradient tape as tape. And then I compute the intermediate state from the encoder. I compute the decoded images using the decoder on the intermediate state. And then the loss value is just this mean squared error function comparing these two. After that, once you've computed the loss value, I collect all the trainable variables, and this is easy to do in TensorFlow. I just get the encoder.trainable variables plus the decoder.trainable variables. And this is a list concatenation, not actually an additive operation. This is for the plotting. So I have this list of the loss values as well as the steps that they correspond to, which will get plotted below. The gradients get computed using this gradient tape. So that's easy. You just get the tape.gradient and you give it the loss value as well as the trainable variables. And the optimizer can apply those. So you zip up the gradients and the trainable variables, and the optimizer will update the networks. And every 25 iterations, I do the same thing, but with the test data set. So I take a random choice from 10,000 images in the test set, and I compute the intermediate state as well as the decoded images and the loss. I get the update the loss history and steps for the validation set, and then I make some plots. So this plotting routine is just going to plot the current step as well as what the loss was for the whole training loop so far on the same plot, and then it updates and displays an input image at random. No, sorry, the first one, and the decoded image, the first one. So if you want to, you can save your weights at the end. I'm going to skip that part. Oops, I missed this block here. There we go. So you should see something that looks like this. It's going to show the loss curve as it trains. And this axis on the bottom is the number of epochs. And on the right side, it's showing you the input image and the decoded image. And I'll let this train for a minute and pause for questions on this. If there's no questions, maybe I'll ask everyone who has been able to run up to this point to raise their hand. Over Zoom, that is. I see one. Terrific. Good. A couple people have succeeded here. So in this plot on the left, you can see the blue curve has been steadily decreasing, and the orange curve has been following along right with it. So that's the validation loss. It says test loss on the plot. It's the holdout data set, whatever you want to call it. That's good. In autoencoders, if you overlearn with your test data set, you will find that you can only encode and decode the objects in that actual trained data set. And then when you run on the test or validation data set, that loss will diverge, and it'll be much higher than the training loss. So you can overtrain an autoencoder. On this particular data set for 10 epochs, it's not really an issue. The train and test losses stay together. You can see that the images start to look quite crisp, and the decoding works well. If you look closely, you do notice obvious differences in some of the sharpness of the decoded images compared to the original images. And as well, sometimes extra features are added. So a 3 might look just faintly like an 8, like we just saw on my screen, or a 7 might look just faintly like a 1. I've seen a 5 turned into a 6. So that's totally possible with the autoencoder. Sometimes those objects get encoded to a similar latent space and then get decoded into similar images. Okay, so mine is almost done. It's at about 9 point some epochs now, and it's going to 10. So I'm going to let it finish, and then we'll move on. Okay, so mine has finished. Looks like the last number was a 5. It did pretty well. If you weren't able to train the model, you can load pre-trained models that went through this training process. Just set this to true, and then you can load the weights, and you'll be able to follow along with the rest of this notebook as well. Okay, so I think one important question about autoencoders is, what's the point? So I mentioned that they're good for data compression, and it's non-linear, and as opposed to principal component analysis, which is a linear algorithm. So you can get much better compression features if you've trained your network well. I like to think of it as you've taken some of the information about your data set and moved it out of the data set itself and into the network weights. It's hard to understand what those weights mean without actually running the decoder steps, but you can move some of the information, and for a particularly big data set, that can be advantageous. When you want to decode an image, the latent state ought to contain all of the information about the input image. And so in principle, that latent state is quite powerful. So if you have a really big data set coming in and you need to do fast analysis on it, your latent state can actually be quite powerful. So if you have, instead of trying to analyze the entire input data, you can transform all of it to a latent state and just work on that if you have the appropriate output model. A lot of people who work on machine learning problems, one of the very first tasks they do is with the MNIST data set, and they do a classifier just to say for a handwritten digit, is it 0 through 9? In this example, I can do a simple classifier as well with just one layer in it, a dense layer, with just 10 units. So this is going to map from the latent space to a 0 to 10 classification, 0 to 9 classification. It's the most simplest model I think I've ever trained with just one layer. And if I initialize it, there you go. You see it has 210 parameters. That's even easy to think about. There's 20 variables in the latent space and 10 output units. Plus there's a bias unit for each one, I believe. Okay, so I'm gonna reload the data set here. And the reason for this is I want to unshuffle it first and get this Y train and Y test values. Since I'm now going to train a classifier, that's a supervised learning technique, and I need to make sure I have the labels as well. But I was shuffling this X train so much that it's totally unshuffled from Y train, so I reload it. We can train this a little bit shorter, so I've just done n epochs. The batch size you can pick as you like. And the training loop is pretty simple. It'll look similar to the other one because I've done all of this plotting as well. I used an Atom optimizer again here, and the loss function this time is this sparse categorical cross entropy. Sparse means that the Y values, instead of being a one-hot vector to represent the class, it's just the index of the class that would be activated in a one-hot vector. That's the sparse feature. And I use this value from logits equals true because I didn't apply any softmax activation here. So you can directly train on the logits without the activation if you pass this parameter properly. Again, we shuffle through the training data, but this time I've captured the indexes and I shuffle the indexes themselves without shuffling the data. That way, when I load the labels, I can get the index based on just looping through this indexes variable. And then I get the same entries from the image set data set and the label data set. So batch images and batch labels. And I reshape it again into this 28 by 28 by 1 shape. That way I can get the intermediate state from the encoder. And in this case, the encoder is not contributing because I'm only going to train on the classifier's trainable variables. So this is trainable, but it's not getting trained in this particular loop. So we fixed the encoder to what we trained before, and we'll do this classification exclusively based on the intermediate state as input and this 210 parameter classifier that I defined. I apply the loss function. Here I pass in the labels and the prediction, which is this classification object. And then I also compute an accuracy, which is just how often is the highest value label equal to the actual label itself. The loss update is almost identical previously, except that I'm only using the trainable variables from the classifier. And this plotting is really similar as well. So I will run this. Instead of plotting two images on the right side, I'm now plotting the accuracy. So it's loss on the left, accuracy on the right. As hoped for, the loss is plummeting, the accuracy is going up, the orange curve is tracking the blue curve. And after a few epochs, this should get to be pretty good. So it's already over 80%. And if you train this to the full 5 epochs, you will see it get over 90% up into the 90 to 95 accuracy range. And if you've done this before in MNIST, you'll know that 90 and 95% accuracy on MNIST is nothing to write home about. In fact, compared to the state of the art on that problem, which is mostly considered a solved problem, it's quite a poor result. But recall that this is only 210 trainable parameters here. So you can see how with this intermediate state that contains enough information for the decoder to decode the image, you also have enough information to classify it. So this network I've trained knows nothing about the handwritten digits. It just learned that the places in this 20-dimensional latent space that numbers have been put represent the original numbers. And it can group them like that and produce a prediction. Another fun application of autoencoders that's not as necessarily useful for scientific applications as the data compression aspect it could be image interpolation. So the latent space is a 20-dimensional space. In this case, if you encode two images and think about the vector between those two images, it does not necessarily represent anything. It could just be random numbers or random noise. But when you start at one end and get to the other end and decode all the numbers in between, you should have mapped your images, your output images from one number to another. So we'll see that here. I'll use the test set. I compute the latent vector over the whole test set, which is quick and easy on a GPU. And then I've just made this loop where you can see for some number of transformations, 10, that's just 10 random points, over 15 steps, move from the first point in the latent space to the second point in the latent space. And that actual computation is just a weighted average of the latent vector for the first point and the latent vector for the second point, where you've just weighted it by how far along this displacement vector that step is. And then I update this image array with the decoder's output for that latent vector that I compute. And I show this as a whole array. So if you run this yourself, you'll see an output like this. And just picking this third column here, this first variable is definitely a 2. The last variable is definitely a 4. And most of the stuff in between is not a number. So you can see that this second one and third and maybe even fourth are similar enough to 2s, same on the other side. That gives you kind of a sense of how much of the latent space around the encoded image, or the encoded point for this 2, still looks like a 2. But if you drift away from this, it looks like nothing. And halfway in between a 2 and a 4, there's just absolutely nothing there. This is kind of, I think this is a fun example of autoencoders, how you can see it transform these images, and it walks through the latent space. Okay. I have one more application from autoencoders, and then we'll take a quick break before getting into generative adversarial networks. So the last application I have is denoising. So an autoencoder is meant to encode the most important features of an image and just throw away everything that's not important to what the true image is. Since noise is generally not an important part of the image, that gets thrown away by an autoencoder. So if you trained on a noisy image and then decoded them, you would generally end up with denoised images. So just to show you this, I've created 2 new instances of these encoders. I've given them a new name so the weights don't get overwritten, and they start out fresh. And I initialize them. And then this training loop is exactly the same as how we trained the autoencoders before, except for one line right here. I'm adding, I guess it's 2 lines. I'm adding random noise to the input images. So I call this tf.random.uniform function, and I pass it the same shape as the batch images, and I just give it a random noise from 0 to 3. So if you recall, the input images went from 0 to 1. So up to 30% of a pixel's value might be noise in some cases. And in fact, for the pixels around the central number, it's almost entirely noise. Everything else here is the same. So go through the intermediate state and get the decoded images, compute the loss, etc. And then let's train this, and you can see what it does. So the top image is now the noisy image, and you can see just by the checkerboard pattern, all of this noise that's piling up. The bottom image is, of course, the decoded image. And again, we're seeing this loss function fall off rapidly. Once you get to about half of an epoch to an epoch, the decoder and encoder pair are starting to do pretty well. And you notice that the noise is basically gone. The images aren't quite as sharp as they were in the previous example. And part of that's because the noise is obscuring the images, the pixels themselves. But you do end up with what I would consider a recognizably cleaned up image of the same original digits that started. So if you have a data set that's noisy, perhaps this is a nice technique you can use if you don't understand just how to suppress that noise. Okay. That was about everything I wanted to say on autoencoders. I'm going to suggest a 5-minute break, and then we get into the generative adversarial networks. If you want to take a few minutes to run through this notebook and change latent space or parameters and ask questions on Slack, now's a good time. I'm going to step out for a minute and come back, and we'll get into the generative adversarial networks. So that'll be at about 3:50 Chicago time, or 4 to 5 minutes from now, wherever you are. Thanks, everyone. Hi again, everyone. I hope if you had a break, get a chance to get a glass of water or use the restroom as needed. I'm going to kick off again with generative models. Again, this is a Jupyter notebook that you can run on Theta GPU. This is a harder problem than autoencoders. Typically, training a GAN gives you better results and is more easily extensible to creating new images rather than just decoding images that you already have. But at the cost of having a much harder training process and sometimes a more unstable training process. So I'll take you through how we create a generative model for MNIST digits again, as well as the details of the training process. And hopefully by the end, you'll be able to run this and understand some of the pitfalls to avoid and get it to work. Okay, so generative models use a totally different technique from adversarial networks. And in the README for this week's session, I've posted a link to the first paper on generative models that you can read. Generative adversarial models. This uses two networks that work against each other. That's the adversarial aspect. One of the networks is called the generator. So that generator will take random input from whatever distribution you want to start with, though it's important that you maintain the distribution kind of as the same distribution over the course of training and inference. And it will take those random numbers and it's meant to output them as images that look like the data set that you're feeding it. So you've pulled some random split numbers and it spits out a 7 or something like that. And you have no concept of where in the data set with the basic GAN you're going to end up in your output of your generator. So there's no controlling whether you get a 1 or a 3 or a 7 or nonsense. And in fact, one of the hardest aspects of GANs is sometimes called this mode collapse, where your generator learns to create a 7 very well. And so it never bothers with any other numbers. So that's just one pitfall. The second network is called a discriminator. The discriminator's task is really simple. It's meant to look at images and you give it some from the real data set and some from the generator. And its only job is to decide on a case-by-case basis, is this number real or is this number fake? And so you pit these two networks against each other. And if the discriminator is doing well, then the generator has to train to do better to trick the discriminator. And if the generator is producing really good images, then the discriminator has to get a little better at separating them. And by going back and forth with this leapfrog adversarial relationship, they slowly get better together. And in the end, you throw away the discriminator and you keep the generator, and it can now take your starting random probability distribution. You can make a draw from that and turn it into an image. And hopefully it's good enough that you no longer need a discriminator and you can extend your data set as you need. During the actual training loop, what you end up doing is some tricks to tell the discriminator. You make it a little harder for the discriminator because it's very easy, as you'll see as it starts up, to tell the difference between a real and a fake image. So I've shown some techniques here that smooth out this training process for a generative network, and you'll see them below. So once again, we start importing all our modules. So I've got TensorFlow as TF, NumPy. The models that we're going to use today don't need to be anything special. So I've got something pretty simple. It's not even as complicated as the previous example. So it's just convolutional layers. They're 5x5 kernels, a couple filters. For the discriminator, we're going to get 28 by 28 size images. So we do this convolution. And then I have a dropout layer, a pooling layer, the same steps, convolution, dropout pooling, convolution, dropout pooling, and then finally a dense layer. And it maps to just one output. And in this case, the output is going to be represented as, let me check my notes so I don't say it wrong, 0 for real, 1 for fake. So the discriminator just has to say, okay, it's 0 or it's 1. The generator, on the other hand, takes some input random noise And in this case, it looks like we'll be mapping it to a 7x7x64 space that gets reshaped into a 7x7 image with 64 filters. And then I do this convolution, upsampling, batch norm, convolution, upsampling, batch norm, convolution, batch norm, convolution. And this convolution at the end, as before, maps it down to just one filter, though it's not a bottleneck. It's a 5x5 kernel, and you output just one filter. And here I apply the same activation as I did with the decoder, the sigmoid activation, to put the output images into this correct 0 to 1 range. All right, so I'll create a generator and some random input. And I've drawn this as uniform input between -1 and 1. And I'm giving it 100 images, or 100 input points. And then I create it through the generator. I can print the summary. Here it is. So it's a little more complicated than our previous networks. It has about 500,000 parameters. And again, some non-trainable parameters. And the discriminator, a little bit less parameters than the generator, so only about 250,000. But you can see that most of them are coming from these, in fact, almost all of them are coming from these convolutional layers. Okay, as before, let's just look at our output images before we do any training. So this is what the generator is creating. It doesn't look like a handwritten digit again. It's between 0.37, 0.61. If you ran this on your notebook, you'll have something totally different. All right, so, okay, 0 to mean fake, 1 to mean real. We read in the data set again. I once again discard the Y values. They're not needed. This was just to check the normalization to make sure that it's correctly mapped from 0 to 1. All right, so here I've created a couple of helper functions to make this training loop a little more comprehensible so we can look at it in pieces. So first is a loss function. This isn't anything special. It's again going to be a sigmoid cross entropy with logits. Here the labels are going to be either 0 for fake, 1 for real, and the logits are going to be the output of this discriminator, which is mapping from 0 to 1. And then I reduce mean over this loss to compute the actual final loss. Fetching a real batch is pretty simple. We just draw random numbers from the MNIST data set, reshape them properly. I return the labels, but they get thrown away, as you see here. And in fact, well, yeah, we don't ever need the labels. All right, so the forward pass, this is the meat of the training loop. So we take in the generator model, the discriminator model, some batch size, some input size for the generator, and this is what's called, I call it the lie rate. So I'll tell you about that in a second. So first thing we do is we fetch a batch of real data and we generate some fake images. So I just pull this uniform function from NumPy, I reshape it to the right size and feed it into the generator. So these fake images will be the same shape as the real data because I've given the same batch size. So here we have a batch of real data and a batch of fake data. Then I make a prediction on each of them with the discriminator. So the prediction on the real data via the discriminator, prediction on the fake data via the discriminator again. And now I start to have to compute losses. So the real labels for the real data are just zeros of the same shape as the batch size. The fake labels are ones. And then the generator gets as well zeros. And I've done this trick here where I've softened the labels. So instead of being all zeros and all ones, this is 0.1, this is 0.9. What this does is, if you think about the way the sigmoid function works, mapping really negative values to 0 and really positive values to 1, this forces the predictions of the networks to be much closer to 0 rather than plus or minus infinity. And what that does is make it a lot easier to move those predictions as you train. And as well, the gradients produced by those predictions are more impactful. So the gradient of the sigmoid function of plus and minus infinity is 0. And the gradient around x equals 0 is much bigger. We also do this, this lying technique. So I disrupt the discriminator. It has a much easier job than the generator. So for some random percentage of the batch size, which is this lie rate times the batch size, I swap the labels. So I take the real labels, and I turn it into 1. I take the fake labels, and I turn it into 0, instead of being 0 and 1. And in principle, this should have some softening here, though I haven't got it. Then I just compute the losses for each data set. So the discriminator real loss is the loss where the logits are the prediction on the real data and the targets is the real labels. And as well, the fake image loss is the prediction, the logits are the predictions on the fake data, the targets are the fake labels. So these look very similar. It's a typo. And then the total loss for the generator, it's the same function, but we take the logits, it's the prediction on fake data, but we're using real labels. So the generator has a different loss, which uses output from the discriminator as well as the target labels. All right, so the discriminator loss gets averaged between its ability to distinguish fake images as fake and real images as real. And then here is just predicting the accuracy. The accuracy is not necessary for training, but we predict how well the discriminator is doing. Okay. And then I return it as these dictionaries where I map the loss for the discriminator, the generator. I return some images of each kind, and I return these accuracy metrics. That's a complicated training process. I'm happy to have questions if anyone has them.
After you play with your comfy rock a little bit,
okay? Okay. Well, if you come up with questions, paste them on Slack and I'll circle back to them. The training loop, in this case, I define a batch size, how many iterations we're going to train for. I take in models and optimizers, which I'll show you, and the lie rate, which is a parameter of the previous function we talked about. I do the same plotting tricks, but now the gradient computation, it does a leapfrog method. So I go through the generator and then the discriminator, and then in the next iteration, I do the generator, then the discriminator, and I call it network each time. And I just do this forward pass. So I'm only computing gradients for one network at a time, but it's the same forward pass each time. So first I get the loss from the generator using that previous forward pass function. And I get the trainable variables from that network, the gradients from that network, and I apply them. Then it goes through and does the discriminator and the whole same thing, get the loss, trainable variables, gradients, apply them. I'm using different optimizers for each network because they have different parameters, and the optimizers will apply and start to learn momentum for the atom optimizer. If you had something like stochastic gradient descent, this might not be necessary. And finally, I do this plotting routine. So let me execute that. And then here's where I actually start to do some training. So I've just defined the models in this dictionary format, the generator and the discriminator. The optimizers are the same here. In previous iterations of this notebook, I've used a less efficient optimizer for the discriminator to make its job a little harder, but this actually works pretty well. So I'm going to run for 2,000 iterations with a batch size of 64, and I pass in the models, optimizers, and the lying rate. So there was a question on Slack. Thanks. I'll read it out for anyone who didn't see it. I didn't quite understand that why were a few labels inverted during the forward pass. Is such a disruption helping in any way for convergence at a later stage? Good question. For this particular model, I've found that it helps in past iterations of this notebook. And if you turn this to 0, you may still get convergence, but also it can diverge quite easily. And by that, I mean, if the lie rate is 0 and you're not flipping labels, the discriminator will get too good too quickly. And suddenly it's unable for the generator to make any meaningful progress. It cannot learn how to make better images quickly enough to keep up with the discriminator. So by introducing this function that sets sort of an upper limit on just how accurate the discriminator can be, you've limited the discriminator. You confuse its gradients each time, and the generator gets a chance to catch up a little more efficiently. I hope that helps. Okay, so I'm going to run this loop. You'll see the losses on the left. The generator is in blue. The discriminator is in orange. The discriminator loss is lower than the generator loss, as might be predicted. The real images are always showing up in the center image here and the fake on the right. And you can see this time there's no one-to-one correspondence. The real image just happens to be any random image, and the fake image is whatever the generator is producing. So the autoencoder was mapping 2 to 2. This is just pulling anything from the data set. Okay, so while this converges, I see there was a comment related to the vanishing gradients problem. That's a good way to think about it. If the discriminator is too perfect, the generator won't have any meaningful gradients. I've seen often the vanishing gradients problem referred to networks that are too deep, and as you apply the chain rule too many times, the gradients go to 0. But it's the same effect. If your gradients are essentially 0, your network doesn't ever learn anything. Great question, thank you. Hopefully, if you're running this on your own interactive node, you're seeing it start to make images that look somewhat reasonable. I encourage anyone who's able to run this to raise your hand on Slack or post some images from your generator on Slack. Sorry, raise your hand in Zoom if it's working. Post images if you get some good ones on Slack if you like to. I'm happy to see as well if you made any changes to the training parameters. Did you get better or worse performance? The way I've set up this training is to slowly anneal this lying rate. So if you run this first one, the lie rate is 10%, then I drop it to 5%, and then I actually drop it to 0%. So the discriminator gets to do whatever it wants in this third iteration. And the losses generally don't change. As the lie rate decreases, the discriminator loss gets a little better. So it starts out here. Well, it looks about the same actually. But I think the images start to improve, the fake generated images. And by the time you've gotten to this third loop in the third iteration of the training loop, the generator should have gotten good enough that it can keep up with the discriminator as it learns fine details and compensate for that. All right, I'm going to run the next one. I saw there was another question on Slack. Let me read this one. Is it because the complexity of discriminator is lower than generator? If making the discriminator more complicated in the sense of parameter size or architecture way, would this be as good as using lie rate? Good question. So I actually did make it a point in the previous parts of this notebook to make the discriminator's number of parameters lower than the generator to give it a little less complexity. If you made it significantly less complex, I think you would get the same initial effects as this lie rate parameter, where you have reduced the discriminator's ability to accurately classify images compared to the generator in early stages. But there's kind of nowhere to go from there. I can turn the lie rate off eventually, but you can't slowly make your discriminator more complex in an easy way. So I think you end up with the same initial conditions, but different final conditions. That's another great question. All right, so it's about halfway through this training procedure. I'm going to let it run. I think the images, the fake images at this halfway point, I actually think look kind of cool. It'll get to 2000, and then we can do one more with the lie rate equals 0. And then I do have saved versions of these. So if you're training these on your laptop or something, and it's taking a really, really long time, feel free to load the weights. This is the save weights function, but go check out how I did it in the Autoencoders notebook. There's a load weights. They're in the GitHub repo as well for the generator and discriminator. And you can load it up and do the rest of this notebook. I saw that Kyle also asked a question earlier. How are autoencoders and Gans used in my field of research? Great question, Kyle. I don't really use autoencoders or Gans. I've had this tutorial for a bit, so I've worked with them kind of in this training context for a while. My own personal research uses techniques like segmentation, surrogate models, and classification, as well as some sort of weird differentiable simulation type techniques that don't really fall under the machine learning categories, but are still based in TensorFlow. All right, I'm going to do the last one with the lie rate of 0. So looking at these plots, the first plot, the discriminator losses is about 0.6-ish, just eyeballing it. The second plot was at about 0.5. This one's coming in at a bit under 0.5. So turning off this lie rate has made the discriminator's loss go down a little bit, making the discriminator a little bit better. And you can see that the generator has been able, as it trains, to compensate for that. The images in this training loop are certainly better than the first training loop. There's a lot of techniques that you can find online in literature for how to train Gans really, really well. And what I'm doing here with MNIST is, sort of super simple. But there's lots of applications that are way more complicated, such as generating faces. So I think there's a cool website like thisfaceisnotreal.com or something like that, where it just serves up generated faces that look real. And that's a kind of a fun application of Gans. In actual research applications, generative networks get used often if you need to create new data. If you have a simulation that's very expensive to run, but you have a lot of data from a detector or some simulation already, you can create a surrogate model with a generative network where you've trained it to generate more data that looks like what you have, but is much cheaper to run. So that's one application of generative networks. That's a great question. According to my experience, how many iteration Gans usually take to achieve acceptable or decent results? I actually want to point out that just defining acceptable or decent results is really hard. So if you look at a face, we as humans are really good at seeing a very poor face and identifying it as such. If you're looking at a scientific data set and you want to generate new images from it, it's really hard to tell whether or not that image is real. One technique I've used in my own research that's not directly related to Gans, but was directly related to comparing data sets, especially with machine learning applications, is if you build some sort of classifier to say, not discriminate real or false, but to categorize the images. So you can do it on the real images 0 through 9, and you end up with that final feature vector. But if you take a step back, you have a pretty big dimensional space up to hundreds of points in that space. And you can compute that penultimate layer for both your real data and your fake data using a classifier that's totally independent of your GAN training loop. And then you can do probabilistic comparisons. You run it for 1,000 real images, and you can take a fake image and compare how likely is that image to be part of the original data set once you've applied your classifier. So you're basically mapping it into a latent space and then doing probabilistic measurements. You still haven't quite gotten to the question of how do you know when it's good enough, but you can at least make quantitative comparisons that's getting better. Yeah, that's a great question. How do we decide to stop training or set the number of iterations? Fantastic question. It really depends on the application. So if you wanted to generate images for to replace your simulation, you would need to train until you have probably a negligible probabilistic difference between your generated images and those coming out of your simulation. Others from LCF might have cool answers on Slack too, and I would welcome them. This person does not exist.com. Exactly. I can pull it up on my screen. These are quite impressive images. Okay. So here it's finished. We've got a fake image that maybe looks somewhere between an 8 and a 0. It's not a great image, but you can kind of justify that it looks similar. If you didn't know numbers from 0 to 9, you might be convinced that this was a real number. So maybe if we do the next version of this tutorial with, Greek letters or something that nobody uses in English, I'll have more convincing fake images. There's a number of things you can do to change these models that might actually make it collapse completely, so it never actually converges. You could try a different activation function. You could try never doing this lie rate. I'd be curious if that causes it to fail still. Turn off the label smoothing. Does it still train? So there's lots of things you can test on this particular model just to play around with the stability of GAN training. In terms of just looking at what the GANs are doing, I find it interesting to look at what happens when you put, say, nothing but zeros in. So I take all zeros, plug it into this GAN, and this is what I get. It looks like an 8. Okay, what about all ones? That looks like nothing. All zeros, while unlikely to be an image, a data point that's been fed into the generator before, is within the target data set. The target space for generating the random numbers. All ones is right on the edge. I was generating random numbers from -1 to 1. So this is really way out there. And then if you're going further and put in all twos, you've got nothing. So this is kind of a reminder that the data set that you feed in has to be consistent. So you can't train with uniform distributions and expect to get good results on the other side. Here's another fun example. If we take 2 points, an initial and final point, similar to what we did before, draw them from this uniform distribution from -1 to 1 100 times, and then vary it like before, you can actually see it from a 7 to something that, well, it's no longer a 7. But you can do this as much as you want. The GANs don't necessarily have the same features where you have crisp images on the outsides and garbage on the inside. You could have real numbers show up anywhere in this space. And in fact, I'm seeing here that I'm getting a 3 in the middle that looks great, and on the edges it doesn't even look so good. There's a lot of follow-up investigations you can do with GANs too. So there's more complicated data sets you can use. You can do more complicated GANs. The networks I built here, in terms of what you use for generative models, were really simple. And that's deliberate. These tutorial sessions need something that you can train in 10 minutes. The ones from NVIDIA, on this person does not exist, they have developed and written papers on very intense training techniques and models that have worked really well for them. Obviously, the results are fantastic. Those people looked very real, but you can make your model sort of arbitrarily more complex. There's also different things you can do with the GANs. So these first 2 papers in the README are the ones that I've based my tutorial off. This generative adversarial networks is using fully connected networks. Then someone came along quickly and said, you can use convolutional networks for this too. This is a really cool technique called CycleGAN, where you can map from one type of image to another. So on their website, they turn horses into zebras, but I've seen people turn pictures into Monet paintings, which is, I think, really fascinating. Not particularly applicable to any of the science I do, but a really cool application in machine learning. There's also other generative techniques that I didn't cover today. I didn't want to overload this session with too many techniques, but I'll just tell you a little bit about them here. So this one's called Variational Autoencoders. This link will take you to an in-depth sort of article tutorial about variational autoencoders. The difference between a variational autoencoder and the autoencoders we trained is in the latent space. So I had said that you can train an autoencoder and where it puts things in the latent space are kind of arbitrary. And each time you train it, it'll be different. A variational autoencoder applies some regularization techniques to the latent space, as well as makes it probabilistic. So instead of just predicting a single vector from an input image, it produces a list of parameters that define probability distributions from which you make a draw that feeds into the decoder. And additionally, there's regularizer terms on those probability distributions to sort of keep them all close together so that you know if you pull out a number that represents a 7, everything close to that you feed into your decoder will also be a 7. Another technique, which is newer and more complicated for sure, is called generative flows. It's this last technique here. This is something that I see getting a lot of traction in scientific applications. I'm a particle physicist by training, so perhaps I just have blinders on to particle physics application. But generative flows have been picked up in particle physics and are outproducing generative adversarial networks. The key difference in a generative flow is that instead of applying a nonlinear network, you're applying invertible functions. As long as they're locally invertible, you apply enough functions, you can map a random set of random images to an output image, and you can go backwards. So they have a different training technique. But in terms of state-of-the-art performance, people at, say, Atlas at the LHC have shown that generative flows can actually mimic their simulation data beyond precision from which they can tell the difference between real simulation and a generative flow. So that's an application that's really taking off in my field, though personally I don't work on that. That brings today's tutorial towards a close. I will stick online, at least on Slack for sure, and I can be on Zoom for questions as well until 5 o'clock or there's no more questions. I would welcome you to try some of these notebooks, change parameters, see if you can break them, and make the networks not converge or converge better. There's some thoughts on what you could do next if you want to further look into generative networks or autoencoders. And there's lots of people in the data science group and further out at LCF who know more about generative networks. I'm by no means the local expert on all of this. We have lots of expertise. So please, ask questions. You'll get lots of great answers. And I thank everyone for their attention today. I hope everything worked for you. And I will stick around for questions. Thank you.